right, so the final category of graph analytics tasks are these pattern matching tasks, and this is where we want to maybe spend a little bit of time, especially because they're somewhat relevant in the news lately with this PRISM system, and I'll try to touch on that in a bit. Okay, so here the idea is to find all instances of a particular subgraph pattern. And so a very simple subgraph here is two vertices that both connect to each other. Okay, and so here you may have conditions on the vertex labels or on the edge labels in order to more precisely specify the exact pattern you're looking for, but you're looking for all instances of this pattern across the graph. Okay, so how many times does this pattern appear in this graph, or what are all the instances in this graph? How can you instantiate this pattern there? Well, here's one from A to B. You instantiate $x equals A and $y equals B, and that seems to fit. And then G to C seems to fit. $x equals C and $y equals G. And then actually, if we're not careful, you have, or perhaps this is what you want, but generally you don't, you'll have duplicates of this, where $x can be B and $y will be A. Whoops. A will be A, and $x will be G, and $y will be C. So there may be 4 instances of this pattern, only 2 of which are in some sense unique. So a popular pattern matching problem is to find the triangles in a graph. And so a triangle is a sequence of 3 vertices that are connected to each other. So A connects to B, B connects to C, and C connects back to A. And so the total number of triangles is a measure of connectedness. There's lots of algorithms to compute this measure to count the number of triangles, and it's a popular challenge problem, kind of benchmark for computer scientists to compare different systems and compare different algorithms. Its utility in practice as far as actually analyzing, getting information out of a graph is not been made so clear to me when I talk to people who compute this. It seems to be more of a good benchmark problem for systems as opposed to a actually informative measure for social network analysis. But that doesn't mean, that's not to say that it's not used ever. So for that reason, I'm not going to go into a lot of detail in the algorithms here, but a key idea to remember here is that a naive algorithm will actually find the same triangle 3 times, right? A connects to B, B connects to C, and C connects back to A, and then B, C, A, B, and then C, A, B, C are all logically the same triangle in that they involve the same nodes, but if you're not careful, you'll find all of these, and so this gives an opportunity to come up with much faster algorithms. I think the other reason why it's studied in a lot of detail is that it's perhaps the simplest possible pattern you can find, and so it's a good starting point to do more complicated pattern analysis. And in fact, the pattern analysis problem in general is a very difficult problem. It's a very expensive problem, which leads to a bunch of approximation techniques. And in fact, even for triangles, there's a variety of algorithms that don't count the exact number of triangles, but give you a good approximation with certain bounds. Okay, so this is a very rich area of research. But I think probably you'd be more interested in the pattern matching problem in general. Okay. And also maybe I'll point out that you can extend this notion to cycles that involve more than 3 vertices, and things change a little bit, but some of the techniques stay the same. So let's look at another pattern match example. This one's a simplified version of a real example that comes from work with some of our collaborators. Okay, so here, given a graph with edge labels is the extension we're going to make. Instead of just source node, source vertex, and target vertex, we're going to assume that there's going to be a label on that edge as well. So a third attribute in this table, if you will. And we're going to be looking at what this label represents is relationships like an object, someone knows someone else, and in this case, drug X interferes with drug Y, and so that label is interferes. So you sort of know what the relationship is, instead of it being a big anonymous relationship, or say in the case of Twitter where you assume that all the relationships are the same, it's just follows, or in Facebook every relationship is just friends, or in the web every relationship is just links to. This one now there are multiple different relationships being coded in the same graph. Okay, and so this is a slightly more realistic case when you're trying to do real data analysis. All right, so here we might say that drug X interferes with drug Y, and drug Y regulates the expression of gene Z, and gene Z is associated with disease W. And so now maybe one pattern that we want to look for is find all drugs that interfere with some other drug that is involved in the treatment of some disease. Okay, and of course you could put other restrictions on here too, or maybe you're looking for a specific disease, or you're looking for a specific drug. But now we're just looking for all patterns of this type. Okay, so pictorially, the query maybe looks like this, where we want to find an edge linking two vertices that's labeled with interferes with, that's then connected to where one of the outgoing edges of that vertex Y is connected to a vertex Z through an edge labeled with regulates, and then that vertex Z is connected with a vertex W that through an edge labeled with associated with. Okay, and we want to find all instantiations of this pattern. All right, so I'm not going to yet talk about algorithms to do this. I want to talk more about languages to express this pattern. And some of you with a database background may already be thinking about how you might do this in SQL, and that's one of the examples I want to show. So the first pattern language I want to consider is SPARQL, which is a query language derived, sort of SQL-like, derived in association with this resource description framework. And you worked with some of this data in the Elastic MapReduce assignment if you completed it. So resource description framework, RDF, defines a formal data model around the idea of triples, which are really just edges in a graph, labeled edges in a graph. And so logically you can think about a table with three columns: subject, predicate, and object. And the subject column refers to vertices in the graph, and the object column refers to vertices in the graph, and the predicate is the edge label. Okay. And so there's a lot of work that went into the formal model to define this, but I think it's most useful just to think of it as a labeled graph. All right. And so the query language ends up looking like this, where you can say select variable names where, and then define these triple patterns. And in this case, all the triple patterns look similar in that they all instantiate the predicate with a actual literal, and all the vertices are variables. But you don't have to do this. You could have a variable in place of the predicate, and you could have literals in the place of the vertex representations as well. Okay. So this says, give me all the x's such that x interferes with y, y regulates z, and z is associated with w. And so if this was actually our data set, then we might return this invented drug named tyrosine, because we can trace a path. Tyrosine interferes with betamin, betamin regulates this gene, and this gene is associated with this disease. Okay. And there might be, billions of these triples. Let me give you another example of a pattern expression language that comes up in database courses in computer science, but is less often seen in industry, although it's starting to make a comeback, which is one of the reasons why I want to mention to you, make sure you're aware of it. Okay, so it's called Datalog, and it's based on a logic programming sort of paradigm, but simpler than general purpose logic programming languages such as Prolog. Okay, so here, to express our query in Datalog, we assume a relation R, which is just the same structure as the triple table we saw for SPARQL. Okay, and I'll show you another formulation in the next slide. So here the pattern, the syntax here looks not all that different than SPARQL. For each predicate, we have an instance of R, and we are looking for, give me all the x's such that x interferes with y, y regulates z, and z is associated with w. And we use three instances of this relation R. And it's essentially can be interpreted as a join. In fact, that's literally how it's going to be implemented in most Datalog systems. Okay, so you're going to join R on y equals y, join R again on z equals z, and then return the instantiations of the variable x. Now, so you've got a relation R with three attributes. Why can't you query this in SQL? And there's no reason. You can query it in SQL. So you can imagine loading this table into a database and rewriting this query like this, where you say a three-way join on the relation R, and I've given them aliases here, I for interferes with, R for regulates, and A for associated with. Then for each one of those relations, make sure you filter to the tuples that correspond to the predicate you're interested in. So make sure the I tuples are only those tuples that have the predicate equal to interferes with, and so on for regulates, and so on for associated with. And then you have to add a couple of conditions for the join. Make sure that the object of the I relation is equal to the subject of the regulates relation, and make sure the object of the regulates relation is equal to the subject of the associated with relation. And then finally just return the subject of the interferes relation. So all these things are equivalent, and that's one of the points I want to make, but I'll come back to that in a minute.